Power isn't always loud. Sometimes it's the gentle turn of a blade longer than a football field, capturing an invisible force. What you see on the horizon is merely the end of the story. The true feat happens much earlier, in a process that combines the scale of pyramid construction with the precision of robotic surgery. This is the complete journey of how a modern giant is erected. From the foundations deep underground to its crowning over 100 meters high. A process where every piece weighs tens of elephants and every mistake is measured in millions. Every colossus needs an unshakable anchor. For a wind turbine, that battle is won underground. The process doesn't begin with steel in the sky, but with excavators in the earth. At the precise location, an enormous cavity is opened. Within this hollow, engineers construct not a simple concrete block, but a system of artificial roots. First, a complex cage of reinforcing steel rebar is woven, forming the internal skeleton of the foundation. At its center, the critical component is placed and secured, the anchor cage or embedded bolt circle. This massive steel assembly, studded with over 100 foundation bolts or anchor bolts, each as thick as a human forearm, is the sole interface between the buried concrete mass and the steel tower that will rise above. It is the structural shoulder upon which the entire weight and dynamic force of the turbine will rest. Then comes the concrete pour, a vast quantity of it. For a large land-based turbine, over 600 cubic meters are pumped in a continuous, uninterrupted operation to fill the excavation and encapsulate the entire steel reinforcement cage. This volume is equivalent to filling half of an Olympic-sized swimming pool in a single, relentless pour. This sea of concrete must then cure and gain design strength over several weeks, transforming into a single, monolithic foundation block weighing over 1,000 tons. It is engineered to resist decades of extreme loading, hurricane-force winds, violent storms, and the relentless cyclic thrust generated by the spinning rotor. While the concrete cures in factories of nearly inconceivable scale, the blades are born. These are not mere components, they are masterworks of aerospace engineering applied to the Earth. Blades come in various sizes, but the true giants can exceed 100 meters in length, stretching longer than almost 2 Boeing 787 Dreamliners placed end-to-end. The process is a meticulous layering of composite materials. It begins with a gel coat applied to the mold to create a smooth, weather-resistant outer skin. Next, layers of fiberglass fabric, the muscle of the blade, are meticulously laid and saturated with epoxy resin. In the critical area near the root, a lightweight core is inserted, often made of balsa wood or a synthetic honeycomb material. This core provides immense stiffness without adding massive weight, functioning much like the web inside a steel I-beam. The two halves of the blade shell are then bonded together using a high-strength structural adhesive. Following assembly, the blade enters a rigorous phase of testing. It is subjected to extreme loads in machines that bend, twist, and fatigue it for weeks on end, simulating an entire lifetime of operational stress in a matter of months. Only those that survive this torture test will leave the factory. A single finished blade for a large offshore model can weigh over 35 metric tons, the equivalent of 7 male African elephants. Transporting these monumental pieces from the factory to the construction site is a masterclass in logistics engineering. Ordinary trucks are useless for this task. Instead, specialized modular transporters are employed, featuring numerous steerable axles that allow the massive load to negotiate seemingly impossible turns. The convoy, often led and followed by pilot vehicles, crawls forward at a walking pace. The journey can last for days. Entire routes are meticulously planned and sometimes physically altered. Temporary power lines may be disconnected and safety barriers might be dismantled to grant passage. Moving a tower section, which travels as a cylindrical segment up to 30 meters long, or an 80-meter blade that protrudes like a jousting lance, is a constant exercise in applied physics and sheer patience. A single misjudged turn can trigger a multi-million-dollar disaster. On site, with all components laid out like a colossal scale model, the erection begins. Here, the crane reigns supreme. This is no ordinary crane. It is a machine that often requires its own transportation convoy and several days to be assembled on location. Its mast rises higher than the turbine itself, and its lifting capacity is measured in hundreds of tons. The sequence is a precise ritual. First, the bottom tower section, a steel cylinder that can weigh 100 tons, is hoisted and carefully lowered onto the embedded anchor cage waiting in the foundation. The massive foundation bolts are then tensioned using hydraulic torquey wrenches that apply a force capable of tearing a car engine apart. Section by section, the tower climbs skyward. Workers, often on platforms at dizzying heights, guide each connection. They may use over 200 high-strength bolts to join two sections, ensuring the structure is perfectly plumb and rigid. A complete tower for a modern turbine can reach 120 meters, the height of a 40-story building. Then comes the critical moment, hoisting the nacelle. This is the brain and the heart of the turbine. Inside this aerodynamic housing, the size of a small house, reside the generator, the gearbox in many models, and all the control systems. This assembly can easily weigh between 70 and 400 tons, depending on the model. Placing it gently atop the tower is an operation that demands calm winds and flawless coordination between the crane operator and the teams on the ground and atop the tower. Finally, the supreme act of balance, installing the blades. Each one is lifted individually. The key lies in the lift point. The crane's hook connects to a special blade lifting yoke that picks up the blade perfectly balanced, keeping it nearly parallel to the ground during the ascent. At that height, installers, working from platforms on the rotor hub, the central forging where the blades connect, manually guide the blade's root end into its mounting interface. It is work that demands nerves of steel, as a sudden gust of wind or a miscommunication could turn the multi-ton blade into a destructive pendulum. Once all three blades are secured to the hub, the iconic silhouette is complete. With the turbine standing erect on the hill, the work is not over. It now enters the crucial commissioning and grid connection phase. The massive cables carrying the power generated in the nacelle descend through the hollow interior of the tower, pass through the foundation, and are buried in trenches that run for kilometers across the landscape to a substation. There, the electricity has its voltage transformed so it can be seamlessly injected into the wider electrical grid that powers our cities and towns. A single one of these modern land-based turbines, with a common capacity of 4 to 6 megawatts, can generate over 15 million kilowatt-hours of electricity in a year at a good site. This output represents enough clean energy to power the annual consumption of approximately 4,000 average homes. The cost of this achievement is significant. The project for a single turbine, encompassing foundation work, manufacturing, transportation, and installation, represents a capital investment of several $million. What remains is a silent testament. A machine that converts the constant whisper of the atmosphere into the tangible pulse of civilization. Its construction is a story of human ambition, of logistical triumphs, and of engineering operating on a monumental scale. It is not a simple process, but every rotation of those blades is the culmination of an extraordinary journey, from the deepest foundations to the capture of the wind at breathtaking heights. Do you believe the enormous costs and complexity of this process are justified by the decades of clean energy these turbines generate, or are there more efficient alternatives we should prioritize instead? Share your perspective in the comments below. We're interested in what you think. If you're fascinated by how the massive engineering feats that define our world are built, we invite you to join the Pastya CDC Creators Club. Here we dive deeper into the processes, innovations, and real stories behind the projects that are reshaping our planet. Subscribe and become part of the community.